Hey guys, we're working with hyperbolas today and we're going to be talking about them. This is section 8.5 and we're doing a little bit of algebra too. Here's our vocabulary today. Our vocabulary starts off with the word hyperbola, and a hyperbola is one of the conic sections that looks like this when it has this kind of an orientation. I'll say this is kind of more of a horizontal orientation, and this one has a vertical orientation, okay? And so when you have hyperbolas that are oriented on your XY axis like this, you're going to find that their foci are located, I'm going to say for laywoman's terms or layman's terms, outside of the hyperbola like that. All right. Now, how do the foci give us any information about where the hyperbola is? I'm glad you asked. So the foci basically create a distance from each point. So let's say I had some point on the parabola, on the hyperbola rather, and I had these two distances from the foci. So let's call this distance 1 and distance 2. The thing about this distance, let's say d2 minus d1, or we could even say the absolute value of d1 minus d2, has to be a certain value. Doesn't matter what point we're talking about. So let's say that certain value is r. So it doesn't matter the point. Any point I choose on the hyperbola, the distance from each foci, when I take the difference of the distance from each foci would still equal, let's call this distance 1 and distance 2, it's still going to equal that r, d1 minus d2 absolute value. All right, and so that's how we get the collection of all of these points. And because we're talking about the difference, we can be talking about the only thing bounded is the difference, but we could be talking about really big numbers. So that's why our hyperbola goes off forever and ever in every direction, because I could be talking about, like, if let's say r were something like 10, I could be talking about 1014, and the other distance could be 1004, right? And so those would be pretty long distances or far distances, such that gives us a collection of a whole bunch of points that are far, far away from, like our usual ellipse that's kind of like, okay, it's just the sum of the two distances that the sum of the two distances from the foci are consistent. That kind of gives us a bounded thing. But when we're talking about the difference, that gives us more of an unbounded situation. So we get this hyperbola. And I hope you had a chance to look at the video that I suggested for you. If you didn't, there's some really wonderful videos on YouTube that you can use to see the applications of some of the conic sections that we've talked about. Each of these guys have a center, and the center would be exactly where you would think, midway, this doesn't look great, but midway between the foci, or even midway between these two parts of the hyperbola. The hyperbola has a vertex. In fact, it has two vertices, and that would be this portion right here. Let me use a different color. How about pink? And so right here, these would be the vertices or the vertex of each part of the hyperbola. The other part of the hyperbola is something that you don't see in the graph. It's called an asymptote. You may remember an asymptote from other equations and other graphs that we've studied before. But this asymptote is one that is not like on the x-axis or the y-axis. It actually is an asymptote, and I brought us down to this figure here. It's actually an asymptote that is drawn by we're going to first make this little rectangle here. Then we're going to draw diagonals in the rectangle. And what happens is our hyperbola will never ever touch these lines, but it gets closer and closer to it. So that's literally, legitimately, the definition of an asymptote continues on forever and ever, where our hyperbola will get closer and closer, but it'll never touch it. So really, this asymptote guides the shape of the hyperbola, but it doesn't actually intersect the hyperbola, okay? Well, because asymptotes don't intersect generally. All right, and then we have something called the transverse axis, and then the conjugate axis. The transverse axis is the axis that cuts right through the hyperbola. So the transverse axis, let me go ahead and highlight that one for you. The transverse axis will be this one in red. Notice it cuts right through the hyperbola. Same thing here. The x-axis is the transverse axis here. The y-axis is the transverse axis here. The center of a hyperbola can be anywhere, so it will not necessarily be the x or y axis as the transverse axis. It could be shifted anywhere just as the center could be. And then finally, the conjugate axis, which I'll do in purple, is the other one, the axis that does not cut through the hyperbola. All right. Okay, so that's a whole lot to sit with. That is a whole lot to sit with, but we need to kind of hold on to that information, and I'm going to do a little close up to talk about something again that we're going to see impacting our problem. So here's one thing I need you to also understand, not just the labeled pieces here, but also look carefully. We have a length A, which is the length from the vertex to the center. We have a length B, which is hard to define because it's kind of like from the center to what exactly? It's the center to the top of this rectangle that we're going to talk about. That's how we get our asymptotes, when we take the diagonals of that rectangle. And then we have the length C, which is from the center to the foci. And notice that in this case, that was the same length before. The center to the foci was the length C in the ellipse. But now, since the foci is outside, in a sense, of the hyperbola, we're going to have a longer C value. And so you may have thought about this, but when we're dealing with a hyperbola, the value A squared plus B squared now equals C squared, much like the Pythagorean theorem, where of course we could write it as C squared is equal to A squared plus B squared, just switching the things around the equal sign. All right, so I want you to keep that in mind, and we're going to go ahead and look at a couple of problems. The first example we have is example 1. We're going to write an equation for a graph. So given this graph, we need to write an equation for the hyperbola shown. Well, let's go back up to this chart. We didn't talk about it, but we should see it. Let's take a look. We notice that the hyperbola has a minus sign instead of a plus sign, right? And interestingly enough, it's x squared over a squared minus y squared over b squared equals 1. And that's when our hyperbola is going to have a horizontal transverse axis, meaning, let me get rid of that, meaning our hyperbola is going to have a shape that looks like this. And here, y squared over a squared minus x squared over b squared, when our hyperbola looks like this. When its transverse axis is vertical. Remember, the transverse axis is the axis that cuts through both parts of the hyperbola, or the vertex of the hyperbola. We're also given that the foci would be located at C0 and negative C0 in this orientation, 0C and 0 negative C in this orientation. The vertices are at A0, negative A0, and 0A, 0 negative A. The length of the transverse axis, the length of the conjugate axis is given as 2b. And I know this still might seem dubious, but we'll discuss it. And the equation of the asymptotes, which are those x values, are given in this situation as plus or minus b over a times x, or plus or minus a over b. So with this, we're gonna use this idea to kind of get to the equation that we're dealing with. So now that I have an idea of the way the equation will be written, I'm going to use the general form of it right here. So I'm using this form to my right because I see that the orientation of the parabola is vertical. So y squared over a squared minus x squared over b squared is equal to 1. Now that we've calculated that, in order to get the equation, I know I need to find a, I know I need to find b, and a and b are related to c, so maybe I'll find c as well. So a is going to be the distance from here to here. And so clearly a is equal to 3. B is going to be some distance that I'm not quite sure about. It's going to be something like this. There's no visual to give me that, and our rectangle can be like this or like this. I'm not quite sure where B is. So I'm just going to indicate it on my graph that that's what I'm looking for, B. The next thing I'm going to do is calculate C. And so C is the distance from the center to one foci. And so C, even though I don't know B, C is equal to 4. Now what did we say? We said this really matches the Pythagorean theorem. A squared plus B squared equals C squared. So I'm going to use this to find B. A squared is 3 squared plus B squared, which we don't know, is equal to C squared, which is 4 squared. So I end up with 9 plus B squared is equal to 16. Subtracting 9 on both sides, I get that B squared is equal to 7. B is equal to the square root of 7. But my formula requires B squared, so the formula specific for this one, this hyperbola centered at the origin, will be y squared over 9, because that's 3 squared, minus x squared over 7, which is equal to 1. So I decided to go to Desmos and plug in the equation that we came up with just to confirm for myself that that made sense, and it seems to, right? Y squared over 9 gives me a minus x squared over 7 equals 1, and we have this graph here that looks an awful lot like this graph here, except, you know, it's red and not blue. But we could even change that. Maybe we can. There we go. All right, let's go ahead and look at another example. So in example 2, we're going to write an equation given the foci and the transverse axis. So the Loran navigational system, or Loran navigational system, is based on hyperbolas. Two stations send out signals at the same time. A ship notes the difference in the times at which it receives the signals. The ship is on a hyperbola with the stations at the foci, or foci. Suppose a ship determines that the difference of its distances from the two stations is 50 nautical miles. The stations are 100 nautical miles apart. Write an equation for a hyperbola on which the ship lies if the stations are at negative 50, 0 and 50, 0. Okay. The first thing I'm recognizing is that we have an orientation that is x squared over a squared minus y squared over b squared, which is equal to, let me get an equal to 1. We need to find a and b. Right now, we don't have either. We have really c, the distance from the center to the edge, which is 50. So I'm going to say that c is equal to 50. And they already told us that the stations were 100 nautical miles apart, so it's 50 nautical miles. I want to find A and B. And so what I'm going to do is imagine this ship driving down, following along its course, where it's going to maintain that the distances from the two stations would be 50 nautical miles. And so when the ship is right there at that point, and I know this is a little tricky, but when the ship is right there at that point, it is still the distance from here minus the distance to here has to be 50 nautical miles. So let's think of it this way. Let me call this D1 and call this D2. So D1 minus, or D1, or I should do D2 minus D1, because in this drawing I have D2 being longer. D2 minus D1 is equal to 50. But more importantly, D2 plus D1 is equal to 100. Why? Because the sum of the two distances have to equal the total distance between the two stations, right? Because I'm on the same axis as both of the stations. And so now this is just a system of linear equations. I'm going to add these two together. That goes away. I've got two D2s, which is equal to 150, which tells me that D2, this distance from here to here, is equal to 75, because I divide both sides by 2. So if I have a 75 here, and then this from here, if this distance is 75, and then this distance has to be 25, then this location, the distance A, has to be 25. Does that make sense? I hope so. So A is equal to 25, and I'm going to have to pick up this question in the next video. I'll talk to you soon. Take it easy. Bye-bye.